Hello everyone. Our today's topic is equilibrium in gaseous reactions, in gas reactions. First of all, in case of gases, important term to discuss is partial pressure. Pressure of an individual gas, either it is present in a mixture or either it is present alone. The pressure exerted by individual gas is called partial pressure. For example, in atmosphere we have nitrogen, oxygen, carbon dioxide, and all of these gases collectively exert atmospheric pressure. Now, the pressure exerted by the nitrogen component is a partial pressure. Pressure exerted by the oxygen gas in the atmosphere is called partial pressure of oxygen, and the pressure exerted by the carbon dioxide is the partial pressure of carbon dioxide, and sum of all pressure is equal to the total pressure. We can write this that PT total pressure is equal to partial pressure exerted by nitrogen plus partial pressure exerted by oxygen plus partial pressure exerted by carbon dioxide plus partial pressures of trace gases, and those gases which are present in a very minute quantity, those gases also exert pressure, and each gas individual pressure is called as a partial pressure. Now, the equilibrium constant expression for the gaseous reaction can also be written just like we have already written Kc for the different chemical reactions indicating concentration. Now, for example, the reaction is ammonia formation in the Haber process. For this reaction, in the similar manner, we will write the equilibrium constant expression Kp. Now here, P stands for the partial pressure, and the P we will use as a symbol of a partial pressure, and the reactant or products are written as a subscript with P, and the number of moles are written as an exponents in the expression. For example, for the formation of ammonia, the equilibrium constant expression is written as Kp is equal to partial pressure of ammonia exerted raised to power 2 divided by partial pressure of nitrogen raised to power 1, because the 1 mole of nitrogen is taken part in the reaction, multiplied by partial pressure of hydrogen raised to power 3, because 3 moles of hydrogen is taken part in the chemical reaction. Now, how we find out the units? On the similar manner, just like we have calculated the units for Kc, the units for Kp can also be calculated. The only difference is, in Kc we use concentration, which was represented by the brackets. Now, in Kp we will not use brackets. We will use instead P for the partial pressure, and rest of the expression will write just like that. Now, if we write down the expression, we can use PA, Pascal to indicate the pressure. Now, as the pressure exerted by ammonia gas raised power 2 is, so the Pascal square will be the pressure units for this ammonia. For nitrogen, we will use only Pascal raised power 1, because the power for partial pressure of nitrogen is 1, depending upon the number of moles present in the equation. Similarly, if we use the partial pressure of hydrogen, then Pascal cube will be taken because it has a 3 power. Now, if collectively we write down, this can be write down in this manner, equal to Pascal square divided by Pascal 4 raised power 4. It means that this power 2 will be cancelled out and only 2 power will left behind. That can be written just like this, 1 over Pascal square. Now 1 over Pascal square can also be written just like Pascal inverse square, or if we mention the unit of Pascal, the unit of Pascals are actually Newton per meter square. If we take Newton per meter square, then we will get as a result unit the Newton inverse square and meter 4 times. This will be the unit for this reaction of ammonia formation and the process. In this manner, we can take any other example. We can write down the Kp in the similar manner, and we will use this expression for the calculations. For example, in the similar manner, we can write the Kp for, if we take this reaction N2O4 will change into 2NO2. Now this is also gas, this is also gas. We can write Kp for this. The Kp for this will be, Kp will be partial pressure exerted by NO2 square over partial pressure of N2O4. If we calculate the units for this reaction, definitely we will have Pascal square over Pascal. It means that Pascal will be cancelled out. 1 Pascal and only a Pascal will left behind for this reaction as a unit that can be represented as Newton per meter square. In this manner, we can use different gaseous reactions to represent the equilibrium constant expression Kp for the gases, and how we calculate their units, that is quite easy. Now, for example, a question is there in the book that hydrogen reacts with iodine in the gaseous state and produce hydrogen iodide. The initial pressure of hydrogen is 7.27 into 10 to the power 6, and the initial pressure of iodine is 4.22 into 10 to the power 6 Pascal. While the product is 0, that's why its partial pressure will also be 0. Now, if we add both of these, partial pressure of these two reacting gases, we will get the total pressure exerted. This can be added just like this. 7.27 plus 4.22. This will give us 11.49 into 10 to the power 6. Because 10 to the power 6 is common, that's why taking common we can add all these values quite easy. This is the total pressure exerted by both the reactant gases. Now, what happens? At equilibrium, they have assigned that the partial pressure of hydrogen iodide comes this. Then the hydrogen iodide comes this 7.72 into 10 to the power 6 Pascal, and at equilibrium, the partial pressure of hydrogen comes 3.41 into 10 to the power 6 Pascal. What is the total pressure of iodine? Now, as we know that in a mixture, the total pressure exerted by both the hydrogen and iodine, that is equal to 11.49 into 10 to the power 6 Pascal. Now, how we will find out the partial pressure of iodine exerted? We know that the total pressure will remain the same as I have mentioned. I have written the formula that Pt is equal to partial pressure of component 1 plus partial pressure of component 2 plus partial pressure of component 3, just like this. Now, if the total pressure is 11.49 into 10 to the power 6 Pascal, then we have the partial pressure of hydrogen 3.41 into 10 to the power 6 plus we have to find out the partial pressure of iodine, partial pressure of I2 plus the partial pressure of HI, which is 7.72 into 10 to the power 6. Now, what we will do? We will add both of these. On adding both of these, we will get the answer as 11.13 into 10 to the power 6 Pascal plus partial pressure of iodine. The total pressure is 11.49 into 10 to the power 6. By subtracting this partial pressure from the total pressure, we will get the partial pressure of iodine. That way it comes out 11.49 into 10 to the power 6 minus 11.13 into 10 to the power 6. Now, what we will get? We will get 0.36 into 10 to the power 6 Pascal pressure of iodine. Now, if we put this value here, 0.36 into 10 to the power 6. Now, all the three pressure values are given at equilibrium, so we can use the equilibrium constant expression to calculate the Kp value for this reaction. That can be say Kp is equal to, we will write down the first equation, partial pressure exerted by Hi square over partial pressure of hydrogen into partial pressure of iodine. Now, we will put the equilibrium value here, 7.72 into 10 to the power 6 square divided by the value 3.41 into 10 to the power 6 multiplied by 0.36 into 10 to the power 6. Now, by calculating all these, we will get the Kp value quite easily. Using calculator, we can calculate the Kp value quite easily. In this manner, using total pressure constant, we can easily calculate the Kp values for such reaction. Now, next is equilibrium in chemical industry. In chemical industry, equilibrium in chemical industry. We have already discussed both of these. In chemical industry, two processes are taking place most frequently. One is oxidation of sulfur dioxide, changing into sulfur trioxide, and second is Haber process, formation of ammonia reacting both of these two gases and what are the conditions? The condition of this reaction is we maintain 450 degree centigrade temperature. These are the optimum conditions. We use V2O5 as a catalyst, and from 1 to 2 atmospheric pressure we exert. What are the conditions here? 450 degree centigrade temperature is the optimum, and we use iron as a catalyst and iron trioxide as a promoter, and we use 200 atmospheric pressure. Now this is also exothermic reaction, and this is also exothermic reaction. Now, above reaction, ammonia produce minus 92 kilojoule per mole energy, while the sulfur trioxide formation gives minus 197 kilojoule per mole energy. Now, we can discuss different factors here. The same factor, if we increase concentration of reactant, reaction will move forward direction, or if we remove the quantity of products from the reaction mixture, then again the reaction will remain in forward direction, and in both the cases we want to produce maximum products to get maximum rate of the reaction. In both the cases, this will remain the same. Normally, in Haber process, we remove ammonia from the reaction mixture. Occasionally, That's why, as a result, the concentration of ammonia remains less in the reaction mixture, and reactants always react together to compensate increase the concentration of ammonia, and reaction remains in forward direction all the time. Next is both the reaction we use catalyst. Catalyst for forward and for backward reaction. It has to just establish the equilibrium earlier than the normal time. Now, the effect of pressure. In case of ammonia synthesis in Haber process, we use very high pressure. Very high pressure. To maintain high pressure, this is a very costly process, and this high pressure is applied just because the hydrogen is a very light gas, and we have to apply pressure to make the collisions of both these gases possible, so that both of these gases react together to produce ammonia. That's why we use high pressure. But in case of oxidation of carbon dioxide, as both the gases are heavier gases, that's why these gases will remain very close to each other. Their number of collisions will also be increased, or just only 1 to 2 atmospheric pressure is sufficient. The most important feature is the compromise over temperature. Now, both these reactions are exothermic, but in both these reactions we increase the temperature to 450 degrees centigrade. Why? We compromise here. Low temperature of the surrounding will favor the forward direction, producing the 100% yield. But in the industry, we compromise on yield, but we prefer the rate of reaction. If we decrease the temperature in both the cases, in this case, if we will decrease the temperature, the catalytic activity of catalyst will decrease. That's why reaction will become slower, and the reaction will become uneconomical. In the similar manner here, if we decrease the temperature, then the bond present between triple bond in nitrogen molecule and single bond in hydrogen molecule is very much strong. That's why these reactant bonds will not break easily. Reactants will not change into the products. Automatically the reaction will become uneconomical. That's why in industry sometimes we compromise the ideal conditions and we prefer the rate of reaction. That's why this is the importance of equilibrium in the chemical industry. I thank you all.